Graphing cubic functions, part 3. This is example 6, modeling real life. The African wild dog is one of the most endangered carnivores on Earth. The estimated population of African wild dogs under human care can be modeled by the cubic function P of t, where t represents the number of years after the year 2000. Use technology to graph the function from 1 to 18, where t is time, so 1 to 18 would be 2001 to 2018, and then it says describe the behavior of the graph on this interval. So we're going to be looking at the end behavior. Describe the behavior. What is the average rate of change in the number of dogs from 2001 to 2018? Do you think this model can be used for years after 2018? Explain your reasoning. All right, to save a little bit of time, it says use technology to graph. So I have went ahead and graphed this function. All right, so if you go to y equals, you can simply type this very long cubic function into your calculator and hit graph. Now, your graph is not going to immediately look like mine. So anytime you have a cubic function that's got these large numbers, well, some of these numbers are small, but numbers that don't fit just typically in a 10 by 10, you're going to have to change the window. Now it says time is from 1 to 18. So we know in our window t is along the x-axis. So in this case, we're going to change our window on the x-axis. I don't need any negative numbers for x because we're not looking at negative time. That doesn't make sense. So we're going to go from -1 up to 20. I have to go at least up to 18. Okay? Since I've only got 20 numbers here, I'm going to use a scale of 1. And then the next one, the y-axis, I had to kind of play with to see, I had to play with numbers to see when I could see the whole function in the window. So I decided I had to go up past 18, so I've got a maximum of 18, and I changed the scale to 100. So when you look here, this is 100, 200, 300, 400, etc., up to 800. And then because this is a scale of 1, this goes from years 1 to 20. This asks us to look from years 1 to 18, but I'll put 1 to 20. So anyways, if you want your graph to look like mine, you're going to have to change your window to match as well. All right, so it says use technology to graph, check. Describe the end behavior. All right, so looking at the graph, we can see that the y values, p of t in this case, I was going to say f of x, but p of t in this case is going down. So because this is a cubic function, we know that the leading coefficient has to be positive because it's got this shape here. So when it's got this shape here, we know that when it's going up to the right, we know that is a leading coefficient that is positive. We don't have to know what the number is, but we know that it's greater than 0. All right, so the end behavior, we can say P of t. When P of t approaches negative infinity, that's because t approaches negative infinity as well. So we're using t instead of x, but let's say x. As x approaches negative infinity, f of x also approaches negative infinity. All right? Now, if you look at the other side, we can say x approaches positive infinity, f of x also approaches positive infinity. And again, for this specific problem, we can say as t approaches positive infinity, P of t also approaches positive infinity. So again, the end behavior would indicate that the model is showing unlimited growth as t or time increases. All right, so the model is valid for a short period of time, but it would not be over a long period of time because unlimited growth, that's not reasonable. So if we look at it between years like 1 and 18, we might get a reasonable model, a reasonable number, but looking at it continuously would not have a logical answer or a reasonable answer. All right, now use technology to graph. Okay, describe the end behavior. Okay, what is the average rate of change in the number of dogs from 2001 to 2018? All right, so remember, average rate of change can be found by doing y2 minus y1 over x2 minus x1. All right, so in this case, we're looking at time. This is our t. This is our x value. So we're going to have t at 1, and we've got t at 18. All right, so basically, we have to find p of t, or our y value. So p of t equals p of t equals. So what we're going to do is substitute 1 into the equation here and find p of t. Then we're going to do it again with the number 18. So plug 18 in to find p of t. All right, now when we do that, when I plug 1 in, I'm going to get 384.418. And when I plug 18 in, I got 693.376. All right, so you may have rounded a little bit differently, but now we have two ordered pairs. We have an x and a y. We have another x and a y. So that means we can plug it into this formula here. All right, so if you need to see it as an ordered pair, just look at it as 1, 384.418. And this ordered pair would be 18, 693.376. All right, so that's our two ordered pairs. So we're going to do y2, 693.376 minus our y1, 384.418, and we're going to divide that by our x values. So 18 minus 1. And then you just simply simplify, and that will give you your rate of change. So our rate of change is about 18.2. All right, so the average rate of change from 2001 to 2018 is about 18 dogs per year, because we're not going to have a 0.2 dog, right? So let's round it to the whole number. So it's about 18, and these are wild dogs, so about 18 dogs per year. We rounded down because 0.2 is closer to 18 than 19. All right, so it says, what is the average rate of change in the number of dogs from 2001 to 2018? So that would be this right here. So this is our average rate of change. And then it says, do you think this model can be used for years after 2018? All right, so I kind of already explained that. For the short term, if you're only looking at it for like the 18 or 20 years, it could be considered a reasonable model. But since the end behavior continues in a positive direction without bound, that means that the growth, unlimited growth, is not reasonable. So that's all for example 6. If you have any questions, please let me know.